Hi, and welcome to this presentation. Today I'm pleased to introduce ELLAS, the first of its kind technology that uses location-based street maps to adapt LiDAR sensing. ELLAS features an intelligent spinning platform that can seamlessly integrate with any off-the-shelf LiDAR. By dynamically adapting the spin rate and sensing parameters to location-specific street maps, we show how ELLAS can significantly enhance LiDAR perception. Before I talk more about ELLAS, let's first hear from Emma the motivation for this work.
Commuting is an unavoidable part of our daily life. Going to school, going to work, and so on. Ensuring safety during these commutes is crucial. In the Netherlands alone, nearly 1,000 people lose their lives each year in traffic-related accidents. Many more endure life-lasting injuries and psychological traumas as a result of car accidents. Many of these tragedies could be prevented. Using the right sensors, vehicles could take proactive measures, such as emergency braking, to reduce road casualties. LiDAR stands out among all automotive sensors due to its exceptionally high angular resolution. Imagine how many casualties could be prevented if every car was equipped with LiDAR. So how come that barely any cars have LiDAR? Well, automotive LiDARs are very expensive, about the price of a low-end car. So unless you are planning to give up a holiday to afford a LiDAR, we've got to think outside the box. Luckily, we've done some of that thinking for you, and the result is ELLAS, our breakthrough that paves the way for affordable LiDARs. By leveraging location awareness, it adapts the LiDAR's range in different directions, ultimately pushing the boundaries of perception. Now I'll briefly explain the physics behind typical automotive LiDARs. What happens is that the LiDAR transmitter emits a laser pulse, which is reflected back of a target and then captured by the LiDAR. By measuring the time delay between the transmitted and the received pulse, the system can calculate the distance to the target, denoted as capital R. Each detected target is represented as a point, as shown by the blue dot. A collection of all these points is what we call a point cloud. In typical automotive perception systems, the LiDAR is mounted on top of a spinning platform, allowing it to emit and detect pulses in all directions, as illustrated here. After completing a full rotation, the LiDAR generates a 360-degree point cloud view of its surroundings. Existing LiDAR systems spin at a constant rotational speed and use the same sensing parameters throughout a rotation. This leads to an entirely uniform maximum detection range in all directions, which, as we'll show, is suboptimal under location awareness. For instance, a standard spinning LiDAR system at a constant speed fails to detect the human shown here. ELLAS addresses this issue by making use of location awareness to enhance the LiDAR's perception. So what do we mean by location awareness, and how is it useful for LiDAR sensing? Vehicles today can figure out their real-time location through GPS. Even before LiDAR scans the scene, the coordinates of stationary objects, such as a wall or a tree, can be determined from a street map. We model this static environment awareness as a function, d static of theta, which denotes the distance to the first static obstacle along direction theta. A sketch of this function at the vehicle's location is shown on the right. I'll now explain how LiDARs can leverage location awareness to smartly sense the environment. Since objects beyond the static obstacle are already occluded, extending the LiDAR's range beyond d-static offers no benefit. So by reducing the scanning range along the directions with closer static obstacles, the LiDAR system can conserve time and use it to sense more critical areas. And that's exactly the key idea in ELLAS, which is to distribute the time resource intelligently over different directions based on d-static map. ELLAS distributes its precious time resources in a rotation by both optimizing the LiDAR sensing parameters as well as the spin rate. These parameters adapt dynamically to the ego vehicle's location and the static environment. What is most exciting about this project is the hardware we built to simultaneously configure the spin rate and the LiDAR over a rotation. When applying the optimized setting to our custom-made hardware, we can see that the LiDAR scanning range extends significantly in directions of interest. This allows ELLAS to detect objects like the person shown here that the standard LiDAR would have missed. Now Timon will tell you how we adapt the LiDAR scanning range.
Thanks, Emma. In this slide, I'm going to explain how a LiDAR scanning range can be adapted. To acquire a single point cloud measurement, a LiDAR fires several pulses in a window called the timing budget. Increasing the spacing between the pulses allows the LiDAR to unambiguously detect distant targets, thereby increasing its maximum range. Furthermore, using several pulses within TB improves the ranging accuracy due to the averaging. In summary, increasing TB extends the LiDAR's range. Now you might wonder, isn't the range adaptation problem as simple as changing TB accordingly to the D-stat map? Well, we will see that it's not that trivial due to the constraint in our system. To understand this, we introduce the notion of dwell time, which is the time spent by the LiDAR on a sector in its field of view. We consider n sectors of equal size, which means each sector covers an angle of 2 pi over n. The range scanned by the LiDAR in sector I is denoted by Ri. To achieve a spatial resolution of delta, the dwell time in sector I needs to be at least this quantity on the right, which is the number of LiDAR points in the sector multiplied by the time needed to acquire a LiDAR point. Here, TB itself is a function of the distance, which is a characteristic of the LiDAR. In our project, we used the VL53 LN1X time-of-flight sensor, and we determined the dwell time needed to scan a sector. As expected, the dwell time needs to be longer to detect targets that are further away. We can interpret the dwell time curve as follows. To detect targets up to a distance of, say, 2.5 meters, the dwell time in that sector needs to be at least 1.5 seconds. Thus, the yellow region comprises feasible combinations of dwell time and range. In ELLAS, we formulate an optimization problem that maximizes the sum of the scanned ranges over the n sectors under 4 types of constraints. First, the scanned range R need not exceed d-stat of theta I in the ith sector. Second, the sum of the dwell times must equal the time period of a standard LiDAR. This constraint ensures that our system operates exactly at the same frame rate as a standard one, for a fair comparison. Third, the dwell time in each sector cannot be smaller than a threshold, which is dictated by the speed limit of the rotor. The final constraint makes sure that the combination of scanned range and the dwell time is feasible. In this work, we take a subset of the feasible region to express our problem as a convex optimization program. The subset is obtained by allowing a safety margin, and this set is encoded as a quadratic constraint in our problem. The solution of our quadratic program comprises the optimized scanning distances and the dwell times for all these sectors. The distances are used to adapt the LiDAR's timing budget, and the dwell times are used to adapt the speed of the rotor. That is omega I 2 pi over n divided by the dwell time. I'll now explain how we realize ELLAS with our custom-made hardware. First, we represent the real-world static topology using a digital map, which is used to model location awareness. In a real-time experiment, the ego vehicle reports its location through QR code-based localization. This location is sent over to a server that runs the optimization problem, which I just discussed. The rotational speeds and timing budgets optimized for this location are transferred back to the ego vehicle. Once this information is received, the Ego vehicle configures its LiDAR system accordingly and obtains a point cloud representation of its environment.
So, welcome to our live demo, and Timon will give us a tour of ELLAS. Before the tour, I'd like to set the stage for our demo. Our little car here, equipped with a LiDAR, drives along this lane. The static environment comprises 2 buildings and 4 walls, and these are programmed in the digital map used by ELLAS. As our car moves, it captures the QR codes on the left to figure out where it is. This location information, along with the static digital map, is then used by ELLAS to configure the LiDAR. And now for the $1 million challenge. We'll introduce a pedestrian right in front of the car and see if ELLAS can detect in time. Note that the pedestrian isn't part of the static digital map and is entirely unknown to ELLAS. Alright, now Timon is going to take the wheel for a test drive.
The robot is controlled wirelessly through a PS4 controller. So if I move the robot a little bit further, the camera will go over the QR codes, scan the localization. There we go. So for instance, for this location, we let the optimization run. So we type Y for yes.
Let's watch the rotation with ELLAS in slow motion. With ELLAS, we notice that the platform spins faster around these buildings and wall 4, thus allowing more time to precisely scan the main lane. To compare ELLAS against a standard system, all we need to do is to program the LiDAR to a uniform profile. And as we just saw here, the LiDAR rotated at a constant speed. Finally, our car wirelessly transfers point clouds acquired with ELLAS and with a standard LiDAR. Now let's see these point clouds from Timon's test drive.
There we get it. And over here we have a result. And as you can see over here, the pedestrian, the green bottle is detected really well compared to the standard LiDAR. Let's now look at the results from our demo. As you can see from this figure, the instantaneous speed in ELLAS varies across different sectors. The speed is higher in sectors where static obstacles are closer and vice versa. Furthermore, the timing budget applied to the LiDAR also varies accordingly. This adaptation results in a higher angular resolution and a longer range along critical directions. Now let's look at the point clouds we get with a standard LiDAR and ELLAS from the same frame rate. When compared to a standard LiDAR, ELLAS results in a higher density point cloud representation of the target. A dense representation is key to the success of object detection algorithms. The standard LiDAR fails to detect the pedestrian here, while ELLAS successfully detects it. Early detection of objects allows higher reaction time, thereby enhancing road safety. Today we showed how location-specific street maps can be used to enhance a LiDAR's perception. Our solution, ELLAS, extends the LiDAR's range along critical directions by jointly optimizing the spin rate and the timing budget at the LiDAR. Due to our low-cost hardware platform, we believe that ELLAS is a game changer in the space of LiDAR sensing. And we are excited to present ELLAS at IEEE Sensors conference in Japan. Before wrapping up, I also want to highlight some of our recent advances in location-aware radar sensing. So, if you are into automotive radars, do check out our papers listed here. And finally, I'm seeking a PhD student to work in radar signal processing. Scan the QR code listed here to apply for this position. Thank you and have a wonderful day.